Hello. In this video, we study how to find the center of mass and moments of inertia of solid regions. Remember that we know how to use double integrals to find the center of mass of a planar lamina and moments of inertia, which is called the second moment, right? Today, we focus on solid regions. Alright, suppose that you have some solid region right here, okay, and you need to find the mass of this. This solid region has density function rho xyz, which depends on x, y, and z, right? The formula of the mass look like this. That is triple integral over q rho of x, y, z dv, right? Let me remind you how to find the mass of a planar lamina, right? And then you can compare with this. If you consider lamina, so the mass is equal to double integral over some r, rho x, y, and then dA. You see that? So basically, when you go from two-dimensional case to three-dimensional case, area goes to volume, function of two variables goes to function of three variables, and the area in R2 goes to some region, solid region in R3. Make sense? So basically, that is very, very common generalization, right? How to do with solid regions. Similarly, we have formulas of the first and the second moments, right? We have the following one. M, Y, Z equal to triple integral over Q x rho x, y, z dv. Let me write out and then I explain about that. The moment with respect to x and y, that is triple integral over q z rho x and y and z dv. And the last moment is with respect to xz, that is triple integral over q y rho x, y, and z dv. So look at this. Since we consider three-dimensional case, right? So you would like to consider the moment with respect to some plane, right? In this case, you have three planes, three basic planes: x, y, o plane, y, z, o plane, and x, z, o plane. Make sense? So when you consider the moment of that solid region with respect to the y, z, right? So basically, you have to consider, this is the y, z, you have to consider the distance. Like for example, from here, you consider the distance from this to the YZ plane. Makes sense? That is nothing but, the x-axis. That is nothing but the x-coordinate of that point. Makes sense? So that's why here you need to multiply by the x. Similarly, if you consider the moment with respect to xy plane, so you need to multiply with the z coordinate right here. All right? So that is the first moment. And then you still have the second moments, the moments of inertia. So you have I with respect to the x equal to q y squared plus z squared rho x, y, z dv, and I with respect to the y equal to triple integral q x squared plus z squared rho x, y, z dv, and I z, that is triple integral of x squared plus y squared in here times rho x, y, and z dv. If you compare these formulas with the formulas for planar lamina, You see why here we use y squared plus z squared, x squared plus z squared, and x squared plus y squared. Okay? For planar laminars, if you want to consider second moment, that means the moment of inertia with respect to the x-axis, so you have to use this formula where y squared is what? That is the square of the distance from that point to the x-axis. So I hope you still remember, right? So if you consider some point right here and you want to find the distance from this point to the x-axis, so you just take this distance, right? But that is nothing but, the y coordinate, right? Or you might consider the absolute. Make sense? So when you consider square of that, you would get y square in here. Make sense? All right, now if you want to consider second moment with respect to the x-axis in three-dimensional case, you do almost the same thing. You have to multiply with the square of the distance from that point to the x-axis, right? So suppose this is x, this is y, this is z, and your point is somewhere in here, right, in the space. You need to find the distance from this point to the x-axis. Okay, so like I take projection of that point onto the x-axis, and then you may think like, yeah, if I consider projection of this point, right, onto the YZ plane, so I have the following one, something like this. Makes sense? So this is the distance, right, because they are parallel. Okay, and then how to find this distance? That is nothing but, y squared plus z squared by the Pythagorean theorem. Makes sense? So that's why you have y squared plus z squared in here. If you consider the second moment of a solid region with respect to the x-axis. Makes sense? Similarly, you have x squared plus z squared in here. That is the distance, the square of the distance from that point to the y-axis. Agree? So I think that is clear enough for the first and for the second moments. Okay, let's solve some examples. In this example, they ask us to find the center of mass of the unit qubit shown in the figure. So we have qubit like this. Here's the one, here's also one, here's also one, right? And the density function at some point x, y, and z is proportional to the square of its distance from the origin. So what does it mean? If you have some point x, y, z in here, you have to calculate the distance from this point to the origin, right? So the distance from x, y, z and the origin is nothing but the square root of x squared plus y squared plus z squared. Make sense? And they say that the density function is proportional. That means the function is just, rho x, y, and z equal to k square root of x squared plus y squared plus z squared. Make sense? Once you have density function, you might find the first moments, and then using the first moments we just find the center of mass. Okay, so I need to find the first moments, but before that we need to find the mass, and the mass is nothing but triple integral over q. We have rho x, y, z and dv. We need to rewrite this integral in terms of iterated integrals. So you would think, yeah, we need to write in dz, dy, dx, or whatever you want. Makes sense? But I choose this order. So I have the following one. From the picture, I see x and y and z are between 0 and 1, right? Are between 0 and 1. And so, when I rewrite this in terms of iterated integrals, because we have cube, which is good. So I just write, from 0 to 1, from 0 to 1, and from 0 to 1. And here we have function k square root of x squared plus y squared plus z squared dx, dz, dy, and dx. I think I mixed something in here. They say that the density function is square, right? It's proportional to the square. So basically, in here we need to apply square. So that is just x squared plus y squared plus z squared. Forgive me about that. So in this integral, we don't have square root. We just have k times x squared plus y squared plus z squared. All right. Now we just integrate with respect to the z for the inside function, and then for the y, and then for the x. Make sense? Let's do that. I have integral from 0 to 1, from 0 to 1. K is constant, so I can take that out. With respect to the z, I have x squared plus y squared times z plus z cubed over 3. This is evaluated from 0 to 1, dy dx. And I plug 0 and 1 into this function. At 0, the function is 0, right? At 1, the function is equal to x squared plus y squared plus 1/3 dy dx. And now we integrate with respect to the y. Okay, we get k integral from 0 to 1. X squared plus 1/3 are constants, so I can write x squared plus 1/3 times y, and then plus y cubed over 3, evaluated from 0 to 1 dx. I plug 0 and 1 into this function. At 0, the function is 0 again, right? At 1, this is equal to k, 0 to 1, x squared plus 1/3 plus 1/3 and dx. So I have k 0, 1, x squared plus 2/3, right? dx is pretty easy because antiderivative of x squared is x cubed over 3 and 2/3 x in here. This is evaluated from 0 to 1. Again, at 0, the function is 0, right? At 1, the function is equal to 1/3 plus 2/3, and that is just k. Make sense? So, again, right, we use the formula, and we need to rewrite that into of iterated integral, right? And then, just step by step, we need to integrate each function. Make sense? Let me show you another way how to solve this problem, because, the function is very special. I want to mention that because maybe we need that in the future, right? In case, if you have simple functions. So, you have k squared, x squared plus y squared plus z squared. So, k is constant, you can take that out here, right? So, you have x squared plus y squared plus z squared inside. I can break this integral into 3 integrals. How about that? So, if I write 0, 1, 0, 1, 0, 1, x squared, dz, dy, dx, plus 0, 1, 0, 1, 0, 1, y squared, dz, dy, dx, plus 0, 1, 0, 1, 0, 1, z squared, dy, dz, dy, dx. Now look at this. In the first integral, you have x squared, right? But you don't have y and z in this function. So basically, similar to the case of double integrals, we can rewrite this as product of 3 integrals. So don't forget we have k in here, okay? I just forgot. I write that is integral from 0 to 1 dz times integral from 0 to 1 dy times integral from 0 to 1 x squared dx. Because you can separate the function, right? You see that? So you can separate. You can write this integral as just product of 3 single integrals. And this is 1, this is 1, and this is 1/3. Similarly, you also have this is product of integral from 0 to 1 dz times 0 to 1 dx times 0 to 1 y squared dy. You see that? So this is also 1/3, right? And you also have 1/3 in here. And then you sum them up, you get just 1. With the k outside, so 1 times k is just k. Make sense? So we found the mass of this solid region, which is the first step, right? Now we have to find the first moments about xy plane, yz plane, and xz planes. Let's find the moment with respect to the yz plane. So that is k triple integral over q x rho x y and z and dA, right? And that is k. We can write 0 1 0 1 in here, 0 1 in here, x squared plus y squared plus z squared dz dy and dx. So you may use the approach I just showed you right here, right? You may separate this integral and you just rewrite that integral as product of 3 integrals. You see that? So let's do this, because you know when you open this parenthesis, you have x cubed plus xy squared plus xz squared. Make sense? And of course you can separate them. All right, so if I write this as sum of 3 integrals, 0 to 1 0 to 1 0 to 1 x cubed dz dy dx plus k from 0 to 1 0 to 1 0 to 1 xy squared dz dy dx plus k 0 to 1 0 to 1 0 to 1 xz squared dz dy dx. The first integral is equal to, here we have only x squared, right? So I write product of integral 0 to 1 dz times 0 to 1 dy and 0 to 1 x cubed dx. You see that? The first two integrals are just 1, right? This is just 1, this is just 1. And this integral is 1/4 x to the 4 evaluated from 0 to 1, which is 1/4. Now let's move to the second integral. So this is equal to integral from 0 to 1 dz, integral from 0 to 1 x dx, integral from 0 to 1 y squared dy. You see? And the first integral is just 1. The second one is, I can write in here, x squared over 2 evaluated from 0 to 1. The next one is y cubed over 3 evaluated from 0 to 1. So this is nothing but, 1/2 times 1/3, which is 1/6. Okay? Similarly, we have this equal to 0 to 1 z squared dz times 0 to 1 dy times 0 to 1 x dx. And this is equal to z cubed over 3 evaluated from 0 to 1. This is just 1. This is x squared over 2 evaluated from 0 to 1. So you have 1/3 in here times 1 times 1/2, which is also 1/6. All right. Overall, your integral is equal to k 1/4 plus 1/6 plus 1/6, which is 7k over 12. And this is the moment with respect to the plane y and z. Right? And similar to the case of planar lamina, if you have the moment with respect to the plane yz, you have the x coordinate, which is equal to this moment divided by the mass. Okay, so I have this moment is 7k over 12 divided by the mass is k. You get 7 over 12. That is the x coordinate. Don't forget that. The x coordinate of center. Okay, and of course, similar to this case, you may find m of x and y, right? And this gives you the z coordinate of the center, which is equal to m xy divided by m, right? And you need to find m of xz in here, so you get the y coordinate, right? The y coordinate of the center, that is equal to mxy over, no, I think this is m of xz because we already have xy, sorry. So xz divided by m. So by doing so, you can find the center of mass, okay? So basically, we need to find the mass first and then, the first moments, all right? To finish this video, we'll solve one more problem on the second moment, or the moments of inertia. Now they give us some hemisphere z equal to square root of 4 minus x squared minus y squared, and they consider some solid region lying between this surface and the xy plane. Okay, so you can imagine we have something like something like this. Okay, and they give us that the density function at some points x, y, z is proportional to the distance between that point and the xy plane. So what is that? The distance between this point and the xy plane is nothing but the z coordinate, right? So I may have the following density function equal to kz. Make sense? All right. We have the density function. Now they ask us to find the moment about the x and the y axis. No problem, we have formulas, right? Let's write it out. The moment of inertia with respect to the x-axis is equal to triple integral over q, where q is this solid region, y squared plus z squared times rho xyz and dv. Okay, so in order to rewrite this integral in terms of iterated integrals, I need to work now. We need to rewrite this integral in terms of iterated integral. So we may choose different orders, but in this case, I will choose the order dz, dy, and dx. That means we need to fix x, right? Fix y, and then we integrate with respect to the z first. So if you fix x and y, that means you fix a point, right? X and y right here. Makes sense? Look at this picture. So if you fix point x and y right here, you need to find the interval of z. And from the equation, z goes from 0 to the point on the surface, right? So that means you have this interval. This is the z, which is f of x and y. Makes sense? So the interval is from 0 to z. All right? I have the following one. The function, I copy y squared plus z squared. Rho is kz, so I write z in here. I will take k out. Okay? The integral with respect to the z from 0 to square root of 4 minus x squared minus y squared. All right, so we're done with the z. After that, we move to the y, right? We move to the y. In order to find the interval of y, I need to graph the planar region in the xy plane. Okay, so look at this equation. Z equal to square root of 4 minus x squared minus y squared. You put z equal to 0, you have the intersection between this surface with the xy plane. So if I put z equal to 0 in here, I have 4 minus x squared minus y squared square root equal to 0. This is nothing but the circle y plus x squared plus y squared equal to 0. And that is the region in the xy plane. Alright? Now, since we choose the order dy dx in here, we need to fix x. I will draw a vertical line. I fix x in here. I need to find the intersection between that line with the circle in order to find the interval of the y, right? So in order to do that, I solve this equation with respect to the y. Here I should have 4. So I have y squared equal to 4 minus x squared, or y equal to plus minus square root of 4 minus x squared. So this is negative 4 minus x squared, and this is positive 4 minus x squared. Okay, so I have the following one I fill in here: negative 4 minus x squared and square root of 4 minus x squared. Finally, I integrate with respect to the x, and from this picture you can see x goes from negative 2 to 2. Make sense? So I write negative 2 and 2 in here. And now we need to integrate those functions. Okay, so let's do that step by step. We have to integrate the inside function first, right? With respect to the z. Okay, so I have the following one. This is equal to k integral from negative 2 to 2 from negative square root of 4 minus x squared in here square root of 4 minus x squared. All right, and then I have y squared z squared over 2, because antiderivative of z is just z squared over 2. And then antiderivative of z cubed is z to the 4th over 4. Okay, plus z to the 4th over 4. This is evaluated from 0 to square root of 4 minus x squared minus y squared. In here you have dy dx, and you plug this value and 0 into the function in the position of z. You have the following one: equal to k from negative 2 to 2 negative 4 minus x squared square root of 4 minus x squared. At 0, the function is 0. At square root of 4 minus x squared minus y squared, I have the following one. I have y squared, just 1/2, y squared times 4 minus x squared minus y squared. Okay, and then plus 1/4 4 minus x squared minus y squared and square, because you have, power 4, right? In here we have dy dx. So we need to evaluate this integral. But before doing that, let's look at one more time the region of integration. That is the circle. And we have experience about this. If we have such a region, it's easier for us to use polar coordinates, right? Because a circle can be described as r greater than or equal to 0 and less than or equal to the radius. In this case is 2, and theta is between 0 and 2 pi. You see that? So I will transfer from rectangular coordinates to polar coordinates, and this integral is equal to k from 0 to 2 pi and from 0 to 2. You see, 0 to 2 pi is for theta and 0 to 2 is for r, right? So we have 1 over 2 right here. Y is r squared sine squared theta, right? And 4 minus x squared minus y squared is just 4 minus r squared. Here plus 1/4 4 minus r squared square. And don't forget to multiply with r when you go from rectangular to polar coordinates. dy, so in this case I have dr and then d theta. Okay, so here we need to pay attention why we have 4 minus r squaring here, because you know this is the y, and we know that x equal to r cosine theta, y equal to r sine theta. So x squared plus y squared is nothing but just r squared. Make sense? All right. Now I will break this integral into two integrals because we have sum, right? So we have k in here from 0 to 2 pi, from 0 to 2. The first one I'll take 1/2 out, okay? So I have r cubed, because r squaring here together with this r, right? We have r cubed times 4 minus r squared times sine squared theta dr d theta. That is the first integral, plus k times 1/4 integral from 0 to 2 pi, from 0 to 2, r times 4 minus r squared dr d theta. Okay, now let's evaluate each of them and then we sum them up, we get the final answer. Look at this. The first integral, you have r cubed times 4 minus r squared and then sine squared theta. So we can separate them. We can rewrite this integral as product of two integrals. Okay, so I have k over 2 in here, product of 0 to 2 pi sine squared theta d theta, and another one is integral from 0 to 2 r cubed 4 minus r squared dr. You see that? It's pretty easy, right? Now let's find each of them. For the first integral right here, I need to use double angle formula, because I know that sine square of theta is 1 minus cosine 2 theta over 2, right? So integral from 0 to 2 pi, 1 minus cosine 2 theta over 2 d theta. And then this is 0 to 2 pi 1/2 d theta minus 0 to 2 pi cosine of 2 theta over 2 d theta. The first integral is equal to pi. It's easy to see. The second one is sine 2 theta over 2 times 2 right here, because antiderivative of cosine 2 theta is sine 2 theta over 2, right? And divide by 2. This evaluated from 0 to 2 pi. And when you plug 0 and 2 pi into this function, you get 0. So basically, this integral is just 0. Overall, we have p right here. We have pi right here. Overall, you have pi right here. Okay? So, this is just pi. Agree? Now, let's evaluate the second one. But that is also easy. You can see that is 0 to 2. We have 4r cubed minus r to the 5th dr, right? We use the power ruling here. The first one is r to the 4, because 4 with 4 will be cancelled already. And here I have 4, I have r to the 6 over 6, right? Evaluated from 0 to 2. At 0, the function is 0, so we need to evaluate at 2. I have 2 to the 4 minus 2 to 6 over 6, which is 16 minus 32 over 3. Okay, so if we simplify that, we get 48 minus 32 over 3, which is equal to 16 over 3. All right, we have 16 over 3. This is right here. So we multiply them together, we have k over 2 times pi times 16 over 3, which is equal to 8k pi over 3. That is the first integral. All right, now let's move to the second integral right here. Similar to the previous case, we can separate because the function depends on r only. So this is nothing but k over 4 and then times integral from 0 to 2 pi d theta times integral from 0 to 2 r 4 minus r square dr. The first integral is just 2 pi times k over 4 right here. So we need to evaluate the second one. So this is equal to 0 to 2 r. I write 4 minus r square as 16 minus 8 r square plus r to the 4 dr, right? So this is equal to 0 to 2 16r minus 8r cubed plus r to the 5th dr, right? And this gives you r square times 8 minus this gives you 2r to the 4 plus r to 6 over 6 evaluated from 0 to 2. At 0 the function is 0. At 2 you get 8 times 2 square minus 2 times 2 to the 4 plus 2 to 6 over 6. Alright, so you have 4, you have 4 with a is 32 minus. You have 32 right here, which is good. And here you have 64 over 6, right? So this will be cancelled out. You get 32 over 3. Alright, so 32 over 3, that is this integral. So I write times 32 over 3. Overall, I will get 2 with the 4 will be cancelled out, so I have 16k pi over 3. Okay, that is the second integral. Now let's sum them up. We get the answer we need. This is the second one. The first one is right here. This is the first one, right? So let's sum them up. Let's write in here 8k pi over 3 plus 16k pi over 3, which is 24k pi over 3, and that is 8k pi. And 8k pi in this case is the second moment with respect to the I. So you can see how long it is. I very encourage you to find the second moment with respect to the y and with respect to the z. Okay, if you have solution, send them to me. Thank you.